When light of suitable frequency is incident on a metal surface, electrons are emitted from that surface. This phenomenon is called photoelectric effect. And today we will be learning in detail about photoelectric effect. Who discovered photoelectric effect? Hertz. You must be familiar with the name Hertz. Where you have heard the word Hertz? Unit of
Unit of
frequency.
frequency.
Yes, unit of frequency is Hertz. So this is Hertz. He did an experiment and he found that whenever light is incident on metal surface, then electrons are ejected out, and these electrons emitted from the metal surface are called, so electrons are emitted out and these electrons are called photoelectrons. Now let us see experimentally what are the arrangements required in order to demonstrate photoelectric effect. So here you can see a experimental arrangement. There is a evacuated glass tube, which is also called a discharge tube, and you have an anode and a cathode. This is the anode and this is the cathode, and here you have a quartz window. Quartz window allow light to pass into this evacuated glass tube, and then there is a photosensitive plate which is kept as a cathode. Now, according to photoelectric effect, when light of a suitable frequency is incident on a metal plate, so this is a metal plate, electrons are ejected out. And how can we know whether electrons are coming out of the plate? You have a arrangement here. This is called a commutator. A commutator is used in order to switch the direction of current. Like if the commutator is kept like this, and if you turn it, this point gets contact with this point and this one gets contact with this point. So you will get one of them acting as the cathode and the other acting as a anode. Suppose here this point is contact with the point here. This is connected to the positive here. And if this is coming into contact with the downside at the same time, if you just twist it, you can get this connected to the downside. So it will be connected to the negative. So if you again twist the commutator, this will connected to downside and this will be connected to the upside. So the potential or the polarity of the electricity changes. So commutator here is used to change the polarity. So you can keep this negative and this positive in the beginning, or you can also change it just by using the commutator. So commutator helps to switch the polarity. Then you have a microammeter. What is the purpose of using an ammeter here? Ammeter will detect current, or it can measure current. So a microammeter is used means it can detect very small currents like microcurrent. Even small amount of current can be detected. So each ammeter will have a range, and this ammeter has its range in microamperes. So few microamperes of current flowing through the circuit can be measured using this microammeter. Then you have a voltmeter here. So this voltmeter will help you to record the applied voltage. And here you have a variable resistance. Why we use a variable resistance? When you change the resistance, the applied voltage will differ. So this variable resistance will help you to vary the applied voltage. So this is the total arrangement. So is it clear to you what are the experimental arrangement we require in order to demonstrate photoelectric effect? Are the parts clear?
Yes, teacher.
Okay. Now, if the potential difference between the plates, so which are the plates C and A? First, we keep C as cathode or negatively charged and A as anode, that is positively charged. So if there is a small potential here and we apply light, what happens is the electrons are ejected out due to photoelectric effect. Now this is anode which is positively charged. So what happens? The electrons get accelerated towards the anode and they move and they complete the circuit. See, otherwise in this evacuated glass tube, evacuated means they have very low pressure. So in this evacuated glass tube, there are no metal wires connecting C and A. So there is no flow of current between C and A. Now, if a small current is measured in the microammeter, it means the electrons from cathode have move towards the anode A. So when light falls on the cathode, the electrons are ejected due to photoelectric effect. And because of the small positive charge here, they get accelerated towards the anode and complete the circuit. And therefore, you can measure current here. Now, if the applied potential difference between the plates, that is between cathode and anode, is increased, the current will also increase. Why the current will increase? If you increase the potential, this will attract more electrons and all these electrons will be able to reach A. So as we increase the applied potential between these two plates, the current will also increase. But it can increase only up to a maximum value called the saturation current. Why it can increase only up to a maximum value called saturation current? Do you have any guess? Why it cannot go beyond the saturation current? Or why only up to a particular value it can increase, not further, even if you increase the applied potential? Any guess? Here, the electrons are produced due to photoelectric effect, right? Once all the electrons produced at the cathode reach anode, there is no more electrons available. So even if you increase the potential difference between them, there are no electrons more to reach A. So that is the maximum value. By saturation current, all the electrons produced at the cathode would have moved to the anode A. So is it clear to you what is saturation current and why it happens? Is it clear to you? No response from you.
Yes, teacher, clear.
Okay. Now, if the retarding potential between the plates is increased, the photocurrent will decrease. So retarding potential means opposing potential. So now suppose you make this C positive just by switching the commutator, you make this positive and this negative. Now for the electrons, the applied potential is retarding because electrons, you know, by nature will be attracted towards the positive plate, not towards the negative plate. Now, you are allowing light to be incident on this plate C and it is slightly positively charged. So the electrons which are produced at C by photoelectric effect will not be accelerated towards A. They will be retarded from A. Why? A has a slight negative charge now. You have changed the polarity. So A have a slight negative charge, so the electrons will not be accelerated. It will be retarded from going towards A. Now, even if you make this slightly negative, still some electrons can overcome that negative potential or can overcome that opposing force and reach A. So there will be a small current flowing. Now, if you increase the retarding potential, if the retarding potential between the plates is increased, if you increase the retarding potential means you make this more and more negative. So it will prevent the electron from coming to it. So if you increase the retarding potential, the photocurrent will decrease and finally stop for a particular retarding potential. That is called the stopping potential. So once A becomes sufficiently negative to oppose all the electrons from coming towards it, and C is sufficiently positive, then the electrons are not able to reach A. So the current will not flow through this micrometer. So what happens? The current is stopped. The photocurrent. Photocurrent means the current produced due to the photoelectric effect, it is stopped completely. And that opposing or retarding potential is called the stopping potential. There is one difference between the potential difference here and here. Here, in the first point, when we discussed the saturation current, C was negatively charged and A was positively charged. So, electrons were attracted towards A. Now, when we are discussing about the stopping potential, what you should note is that C, where the electrons are produced, are now positively charged and A is negatively charged. So it is retarding the electrons. So all these electrons will get retardation or it won't be allowed to move towards A by increasing the retarding potential. So no more electrons reach A and the photocurrent is completely stopped. So the potential at which the photocurrent is stopped is called the stopping potential. So is the concept of stopping potential clear to you? Is the concept of stopping potential clear to you? I need a response.
Yes, teacher, clear.
Okay. Now, let us see what happens when light falls on this plate. When light falls on this plate, the light has some energy, right? So you know that light is a beam of photons. So what happens when light falls on the plate? They kick out the electrons. So they will give kinetic energy to the electrons. So what is the maximum kinetic energy of the electrons? Maximum kinetic energy of the electrons is E times V naught. E is the charge of the electron. V naught is the stopping potential. Stopping potential means when you apply potential, the electrical energy that reach here is E times V naught. Charge of the electron times potential. Charge into potential will give you energy. So this is the applied stopping potential. So when the electrons are no longer allowed to come here means the applied potential balances the kinetic energy of the electron. So the value of the kinetic of energy of the electron is the maximum value of kinetic energy of the electron will be equal to the applied potential energy, whatever is given here, that can oppose. So the maximum kinetic energy obtained by the electron will balance with the electrical energy. Maximum kinetic energy is equal to E times V naught. So half mv, m means V maximum. So this refers to the kinetic energy of the electron and Vm refers to the maximum value of the velocity of the electron. So half mv square is equal to E times V naught. This is the balancing situation at the stopping potential because V naught is the stopping potential, E is the charge of an electron. Now, what is observed experimentally is that If the intensity of light is increased, the stopping potential will remain unchanged. So the intensity of light has no effect on the stopping potential, but the photo current will increase. So note down this, remember this experimental observation. We will now try to explain this experimental observation first using the classical concept of light as an electromagnetic wave. Then we will try to explain these experimental observations using the quantum concept of light as a photon. Let us see which explanation wins, or which theory, the classical theory or the quantum theory, which one is able to clearly explain these experimental observations. So let us see what are the two major experimental observations. One is that if the intensity of light is increased, the stopping potential will remain unchanged. So intensity of light has nothing to do with the stopping potential. But if the intensity of light is increased, the photo current will increase. So intensity depends on the photo current. So if you increase the intensity of light, the amount of photo current or the current measured using this microammeter will be more. Second point to be noted is that if frequency of light is increased, the photo current will remain unchanged. Means frequency of light has nothing to do with the photo current, but the stopping potential will increase. So intensity is related to what? Current or voltage? Current or stopping potential? Intensity is related to current, not to stopping potential. Frequency of light, it is related to photo. It is not related to photo current or the current, but it is related to the stopping potential. Is that clear to you, these 2 points? You have to remember this. We will see why it is so. Is that clear? Can I go to the
Yes,
next
teacher.
slide? Okay.
Yes,
So
teacher.
remember these 2 points. Now, just whatever experimentally we have observed, we are going to discuss that with more clarity using graphs. So what are the characteristics of photoelectric effect? First of all, photoelectric effect is instantaneous. Instantaneous means the moment light falls on the metal plate, electrons are ejected out. There is no time lag between the light falling and the electrons coming out. It happens at the same time. It is instantaneous. Now, the kinetic energy of photoelectrons depends on the frequency of the incident light. Like we saw in the previous slide that the kinetic energy depends upon stopping potential. And when the frequency is increased, stopping potential is increased. So we can conclude that the kinetic energy of the photoelectrons depends upon the frequency of the light, but not on the intensity, because we saw that if you increase the intensity, there is no effect on the stopping potential. So kinetic energy of electrons depends on the stopping potential. So it depends on the frequency of light, not on the intensity of light. Then for a particular frequency of light, a retarding potential difference of photocurrent is proportional to, and okay, for a particular frequency of light, which means for a constant frequency and retarding potential difference. So if you keep the frequency constant and also the retarding potential difference constant, the photocurrent is proportional to the intensity of incident light. It's same as telling that the photocurrent depends only on the intensity of light. As the intensity is increased, the photocurrent is increased when you keep the frequency and retarding potential constant. Now, for a fixed frequency and intensity of light, the photocurrent will decrease with the increase of retarding potential and become zero at a stopping potential. This is what is meant by stopping potential. We told that when you increase the retarding potential, what happens? The photocurrents gradually reduces and it stops coming. The electrons stop reaching the anode. This is because the stopping potential have stopped the electrons from coming to the plate. So the current cannot be there. So the photocurrent will decrease with the increase of retarding potential. Now, another interesting fact which is observed is that for each metal, there is a minimum frequency. Okay, I typed this by mistake. There is a minimum frequency of light called threshold frequency, below which no electron will be emitted from the metal, whatever be the intensity of light. So when you are making the light fall on a plate, suppose you are giving a frequency, say 10 hertz. This is not an exact value. I'm just giving you an arbitrary value, 10 hertz. Then this plate will not give the photoelectric effect. Now, if you put it 12 hertz, okay, the plates start giving photoelectric effect. So there is a minimum frequency. If you go below 12 hertz, suppose the plate is not giving photoelectric effect. Okay, so there is a minimum frequency. Even if at 10 hertz you increase the intensity of light how many times, there is no photoelectric effect. But at 12 hertz, even if the intensity of the light given is very small, there is photoelectric effect. So there is a minimum intensity which is particular to a plate. Suppose for this plate C, it is 12 hertz. If you take another plate, say D, then it will be another value, maybe 20 hertz. So for each metal, the value of that minimum frequency below which no electron will be emitted will be different. So this minimum value of frequency is called the threshold frequency. We will learn more about it. Now let us have a look at each of these graphs. So here you have a graph that shows the variation of photocurrent with intensity of the incident light. So here you have taken along the y-axis photoelectric current and the intensity of light. As we told before, as the intensity of light increases, photocurrent increases. Now here you have another graph showing the variation of photocurrent with applied potential difference or different frequency of incident radiation for different frequencies. So here you have the applied potential. We told that as the applied potential increases, photocurrent also increases. But after reaching a saturation current, even if you increase the applied potential, what happens? The current is not increasing. See here, the saturation current, which means all the electrons that are produced at plate C have now reached A. Now, no more extra electrons to reach A. So there is no point in further increasing the potential. So this is it. As you increase the applied potential, the photocurrent increases and reaches a maximum value called the saturation current. Now this direction, in the opposite direction, you are applying retarding potential, which means you are opposing the electrons from coming to the plate A. So as you increase the retarding potential, what happens? The photocurrent reduces and finally stops. And this potential at which the current stops is called the stopping potential V0. Now see, V0 varies with frequency. This is not V, this is nu. In your textbook for frequency, the letter F is used, but in most books you can see for frequency, a symbol nu is used. So this is nu1, nu2, nu3, referring to three different frequency. See, as we change the frequency, the stopping potential changes. We told that before that As we change the frequency, the stopping potential changes. So the stopping potential or the retarding potential at which the current stops depends upon the frequency. For different frequency of radiation, the stopping potential is different. So that is shown by this graph. Is this graph clear to you? Is this graph clear to you?
Yes, teacher.
Okay. Now let us see how the variation of photoelectric current occurs with potential difference. So here you have photocurrent, right? Here I1, I2, I3 shows three different intensity. This is a graph which shows the variation of photocurrent with potential for different frequencies. Here it shows that the stopping potential varies with frequency. This graph shows the variation of photoelectric current with potential, but not for light having different frequency, but for light having different intensities. See, as we have learned, as the potential increases, current increases and reaches a saturation current. And as the retarding potential increases, the current decreases and reaches a stopping potential. See, for different intensity of light, the stopping potential is the same, but the saturation current is different. As we learned before, as the intensity changes, the current, photocurrent or the saturation current changes, but it has no effect on the stopping potential. So it's again repeating the same concept that when you changes the intensity, current changes, stopping potential doesn't change. But when you change the frequency, the current doesn't change, it remains same, but the stopping potential changes. So this is the difference between this graph and this graph. This graph shows for different frequencies. This graph shows for different intensity of light. Now let us look into this graph. What does it say? It's the variation of stopping potential with frequency of incident radiation. See, nu naught or F naught is the minimum frequency from which the photoelectric effect will start. So before this frequency, there is no photoelectric effect. No photoelectric effect. There is no stopping potential, nothing. So before this threshold frequency or the minimum frequency, at less than that frequency, there is no photoelectric effect. But at the threshold frequency or the minimum frequency, the photoelectric effect will start, and as the frequency increases, the stopping potential also increases. So, see, now let me ask you one thing. Nu1, Nu2, Nu3, which will be a higher frequency? Nu1, Nu2, Nu3, which will be higher frequency?
mu1.
Nu1 will be higher frequency. Let me see. We saw that as the frequency increases, the stopping potential increases. Here you have the stopping potential minus V naught, then minus V2, minus V3. You told Nu1 will be more because it's a negative quantity. So you thought that minus V naught will be bigger than minus V naught 3. Is that the reason?
Yeah.
I want to correct you here. Retarding potential. Here, the frequency depends upon the value of the potential, not on the sign. Retarding means just opposing. Suppose this is minus 2, this is minus 4, and this is minus 6. So the frequency depends upon the magnitude of that potential only. So nu3 is the highest frequency. Is that clear? Retarding potential, you should not consider the sign negative there. The value of the retarding potential, 6 is more than 3, or 6 is more than 2. You know that, right? So nu3 is the highest frequency. Here it refers to the magnitude of the stopping potential only. This is why I asked you this question, because I know that some of you will be thinking in that manner. So the frequency depends upon the potential. As you increase the frequency, the stopping potential increases, means the magnitude of that stopping potential increases. You should not consider the negative sign here. Is that clear now? Okay, now tell me which will be higher frequency. Nu1, nu2, nu3.
Nu3.
Nu3. So here when we refer that, tell that as the frequency increases, the stopping potential increases, means the magnitude of that value, the applied potential is increasing. Don't get confused with that negative sign. Okay. So now let us see how electromagnetic theory or classical electromagnetic theory, which consider light as a wave, light as an electromagnetic wave, try to explain the characteristics of photoelectric effect, but they fail. So let us see what are the explanations, or what are the ways in which, if you consider light is an electromagnetic wave, we are trying to explain the photoelectric effect and how it fails. According to classical wave theory, some time is needed for the emission of electrons from a metal plate due to the fall of light on it. See, according to classical electromagnetic theory, light is a form of wave. So, wave means a continuous flow of energy. So, it takes some time for an electron to absorb enough amount of energy and come out of the metal. Because you know that the electrons are bound in an atom. So are when they exist in a metal. So each electron, they will be receiving the light rays if it is coming as a wave, which is a continuous flow of energy. So it will wait till it gets enough amount of energy and come out. So classical electromagnetic theory will definitely expect a time lag. But experimentally, it is observed that there is no time lag. The moment light falls on the metal, electrons are kicked out. So, classical wave theory fails to explain why photoelectric effect is instantaneous, why there is no time lag between the fall of light and the coming out of electrons or the emission of electrons. So this is one way the classical electromagnetic wave theory fails to explain what is experimentally observed. Now we will discuss more about this, the limitations of electromagnetic theory, and also how quantum theory successfully explains photoelectric effect in the next class. Okay.